There's something utterly mesmerizing about staring up at the night sky, knowing that every flicker of light is a story, a mystery, a cosmic puzzle waiting to be unraveled. And among those countless points of brilliance, there's one galaxy that stands out not just for its beauty, but for the sheer strangeness hiding within its spiral arms. Meet the Pinwheel Galaxy, also known as Messier 101, a swirling masterpiece of stars and dust that's home to some of the most baffling phenomena astronomers have ever witnessed. This isn't just another pretty face in the cosmos. It's a treasure chest of enigmas, each one more puzzling than the last. Imagine a place where stars vanish without a trace, where ghostly radio signals pulse with no clear source, and where entire clusters of celestial objects behave in ways that defy every rule we thought we knew. That's the Pinwheel Galaxy, a place where the universe seems to be playing by its own bizarre rulebook. From unexplained eruptions of energy to celestial objects that move in impossible patterns, this galaxy is a hotbed of cosmic oddities that leave even the sharpest scientific minds scratching their heads. And today, we're diving deep into 30 of its most jaw-dropping mysteries, each one a reminder of just how little we truly understand about the cosmos. But why does this matter? Because every strange phenomenon we uncover in the Pinwheel Galaxy isn't just a curiosity, it's a clue that could rewrite our understanding of physics, of star formation, even of the very fabric of space and time. This journey isn't just about marveling at the unknown. It's about stepping to the edge of human knowledge and peering into the abyss where the answers might just change everything. So buckle up. By the time we're done, you'll never look at that tiny, twirling pinwheel in the sky the same way again. The Pinwheel Galaxy isn't just another distant smudge of light. It's a living laboratory of cosmic weirdness, and we're about to take a front row seat to its greatest hits. From the inexplicable to the downright eerie, these 30 phenomena will challenge what you think is possible, leaving you with one burning question. What else is out there waiting to be discovered? The universe is stranger than we can imagine, and the Pinwheel Galaxy is here to prove it. Let's begin. Right there, in the outer reaches of the Pinwheel Galaxy, something impossible lurks, a ghostly spiral arm that shouldn't exist. Astronomers call it the Phantom Arm, a faint, wispy stretch of stars and gas curling through space like a cosmic afterthought. But here's the twist. According to everything we know about gravity, this structure shouldn't hold together. The math says it should have unraveled eons ago, scattered into the void. Yet there it is, defying the laws of physics with every silent revolution around the galaxy's core. What could keep such a fragile structure intact? One leading theory points to dark matter, the invisible glue of the universe. Imagine an unseen hand, a hidden scaffold of dark matter woven through the arm, anchoring it in place against the tidal forces that should have torn it apart. It's as if the galaxy is wearing a cloak we can't see, one that bends the rules of reality itself. But there's another possibility, just as wild, a cosmic collision. Billions of years ago, the pinwheel might have brushed against another galaxy, a near miss that sent ripples through its structure, stretching stars into this eerie, lingering trail. Telescopes have captured the Phantom Arm in haunting detail, a pale whisper against the bright swirl of the pinwheel's main arms. Side-by-side images show the stark contrast, where the galaxy's primary arms blaze with young, blue stars and pink nebulae. The Phantom Arm is a graveyard of older, dimmer stars, its gas stretched thin. It's like comparing a roaring bonfire to the last embers of a dying flame. Yet somehow, against all odds, those embers keep burning. This isn't just a curiosity, it's a crack in our understanding of how galaxies evolve. If dark matter is the culprit, it challenges how we model its distribution. If it's a collision relic, it forces us to rethink how delicate these cosmic dances can be. The Phantom Arm doesn't just haunt the Pinwheel Galaxy, it haunts our textbooks, whispering that the universe still has secrets we've yet to uncover. Deep within the Pinwheel Galaxy's spiral arms, astronomers have spotted stars behaving like cosmic fugitives racing outward at speeds so extreme, they're practically tearing free of the galaxy's gravitational grip. These are hypervelocity stars, celestial projectiles hurtling through space at millions of miles per hour, and their existence defies everything we thought we knew about how stars move. Normally, stars orbit their galaxies in predictable, graceful arcs, bound by gravity's invisible tether. But these renegades, they're on a one-way trip into the void, and the only explanation is something incredibly violent, or incredibly massive, flinging them outward like stones from a slingshot. Chandra X-ray Observatory's data reveals the smoking gun, trails of high-energy radiation left in the wake of these fleeing stars, clues pointing to an unseen architect behind their escape. The leading suspect, a hidden intermediate mass black hole lurking in the galaxy's heart. Unlike the supermassive black holes we often hear about, these middling monsters are elusive, rarely spotted, but packing enough gravitational punch to send stars careening into oblivion. Picture a cosmic game of billiards. As a star drifts too close, the black hole's immense gravity whips it around in a deadly dance, then flings it outward at speeds that boggle the mind. Animations of this slingshot effect are both mesmerizing and terrifying. A star approaches the black hole in a graceful curve. Then, in a blink, it's catapulted away, its path now a straight line cutting through the galaxy like a bullet. The energy involved is staggering. Some of these stars reach velocities over 1,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 7 minutes. And once they're gone for good. These stars don't loop back. They become interstellar nomads drifting through the darkness between galaxies, their light fading into the abyss. But here's the real puzzle. Intermediate mass black holes aren't supposed to be common. We've found plenty of small stellar black holes and gigantic supermassive ones, but these middleweights, they're the universe's missing link, and if one's hiding in the Pinwheel Galaxy, it could rewrite our understanding of how black holes form and grow. Each hypervelocity star is a breadcrumb, a clue leading us closer to confirming this cosmic fugitive's existence. And if we find it, the implications are huge. It could mean galaxies like ours are littered with these hidden gravitational monsters, silently shaping their surroundings in ways we're only beginning to grasp. The Pinwheel Galaxy's hypervelocity stars aren't just a spectacle, they're a challenge to our models, our assumptions, even our place in the cosmos. Because if stars can be hurled into the void so easily, what else might be lurking in the shadows, waiting to upend what we think we know? The universe loves a good mystery, and in the Pinwheel Galaxy, it's written in the stars, literally. Among the Pinwheel Galaxy's strangest quirks is a phenomenon that feels ripped straight from a sci-fi thriller, supernova, that refuse to fade into the cosmic background. Instead, they leave behind ghostly echoes, their light bouncing off interstellar dust and returning to us years, even decades after the initial explosion. Take the case of Supernova 2011 FE, a stellar detonation so bright it outshone its entire host galaxy. Astronomers watched its light fade, as expected, only for telescopes to later capture eerie, repeating flashes from the exact same spot, like a cosmic déjà vu. These aren't new explosions, they're delayed reflections, light that took the scenic route through the galaxy's dust clouds before finally reaching us. It's as if the Pinwheel Galaxy is taunting us with whispers of its dead stars, replaying their final moments in slow motion. But the plot thickens. When scientists combed through the aftermath of these supernova, they found something even more baffling: nothing. No neutron stars, no black holes, just empty space where a dense stellar corpse should be. Every textbook tells us that when a massive star dies, it leaves behind a remnant, either a crushed neutron star or a gravitational pit so deep not even light can escape. Yet in the Pinwheel Galaxy, some supernovas seem to vanish without a trace, as if the star's core simply disappeared. It's like finding a murder scene with no body, just a chalk outline and a pile of unanswered questions. Compare this to a typical supernova aftermath, like the Crab Nebula's pulsing neutron star spinning relentlessly at the heart of its wreckage. That's what we expect, a visible, energetic remnant, a fingerprint of the explosion's physics. The Pinwheel's missing remnants defy that logic. One theory suggests these stars might have collapsed into black holes so stealthy they've left no detectable trace. Another possibility, the explosions were so violent they obliterated the core entirely, scattering it into particles we can't yet observe. There's even a fringe hypothesis that some of these stars didn't die, they were hurled out of the galaxy entirely, flung away by some unseen force before they could leave their mark. The implications are staggering. If supernova can occur without leaving remnants, it challenges our fundamental understanding of stellar life cycles. These echoes and absences aren't just cosmic footnotes, they're clues that the universe might have more exit strategies for dying stars than we ever imagined. And in the Pinwheel Galaxy, every flicker of light, every empty patch of space is a reminder. The cosmos still holds cards it hasn't shown us yet. Then there's the eerie symmetry of it all, the way these echoes mirror the missing remnants like two halves of the same unsolved riddle. The light that lingers and the cores that vanish might be connected by physics we're only beginning to grasp. Perhaps the same forces that scatter a supernova's light into echoes also disrupt the formation of a stable remnant, leaving behind a cosmic magician's trick. Now you see it, now you don't. Until we crack this code, the Pinwheel Galaxy's dead stars will keep haunting us, their afterimages flickering across the void, their final secrets still locked away in the darkness. Now let's turn our attention to one of the most baffling radio whispers drifting from the Pinwheel Galaxy, a colossal, looping structure of energy with no apparent origin. Stretching hundreds of light years across, this eerie radio emission forms a near-perfect arc, like a cosmic lasso flung into space. Radio telescopes first caught its faint signature, a steady hum of low-frequency waves, but when astronomers pointed optical instruments at the same coordinates, they found nothing. No stars, no galaxies, not even a wisp of gas dense enough to explain the emission. It's as if the universe left a cryptic voicemail, then hung up without leaving its name. So what could possibly power such a structure? One theory points to the ghost of a quasar long gone dark. Quasars, the blazing cores of distant galaxies, often shoot out colossal jets of particles at near light speed. If the Pinwheel Galaxy once hosted a quasar that's since gone dormant, those jets might have collapsed, leaving behind a relic loop of charged particles still glowing faintly in radio waves. Picture a bonfire reduced to embers. The flames are gone, but the heat lingers. Another, far wilder idea involves dark matter specifically. The notion that particles of this invisible stuff could be annihilating each other in concentrated pockets, releasing bursts of energy that manifest as these mysterious loops. It's like an unseen fireworks show detonating in the darkness between stars. The evidence is as tantalizing as it is sparse. Radio images overlay the pinwheel's visible spiral arms with this faint gossamer loop, and the mismatch is jarring. Where the galaxy's stars and gas follow graceful curves, the radio arc cuts across them at an odd angle, as if drawn by a different hand. Some researchers argue it could be a fossilized shockwave from a past galactic collision, a ripple frozen in time. Others suggest it might be the fingerprint of a primordial magnetic field, woven into the fabric of the galaxy itself. But here's what truly keeps scientists up at night. If this loop isn't tied to any visible object, how many others might be out there, lurking just below our detection thresholds? The Pinwheel's Enigma hints at an entire hidden layer of cosmic activity, one we're only starting to sense. Every unanswered question about this radio loop isn't just a gap in our knowledge. It's a window into the universe's quietest, most secretive corners, where even emptiness hums with stories waiting to be heard. At the heart of the Pinwheel Galaxy, where most spiral galaxies would show a chaotic tangle of dust and gas, astronomers have stumbled upon something that defies expectations. A series of dust lanes arranged with uncanny precision, forming near-perfect diamond shapes. These aren't the usual wispy, organic tendrils we see in most galaxies. These are sharp, angular structures, as if someone took a cosmic protractor and etched geometric perfection into the cosmos. It's a sight so unusual that when researchers first spotted it, they double-checked their instruments, convinced it had to be an artifact. But the data didn't lie. The Pinwheel Galaxy's core is a cosmic art gallery, showcasing dust lanes folded into shapes that seem almost intentional. What could sculpt dust into such rigid forms? One leading theory points to the galaxy's magnetic field's invisible lines of force that might be acting like celestial cookie cutters, shepherding particles into these bizarrely orderly patterns. Imagine running a comb through tangled hair. The magnetic fields could be doing something similar, aligning dust grains along their lines with such precision that the chaos of space takes on a strange mathematical beauty. But there's a twist. The strength of these fields would need to be off the charts, far beyond what we've measured in other galaxies. Could the Pinwheel be hiding a powerhouse of magnetic energy at its core, one we've yet to fully detect? Then there's the bar instability angle. Most spiral galaxies have a central bar, a straight, dense structure of stars that can influence how dust and gas move. Normally, these bars create messy, turbulent flows, but in the Pinwheel, simulations suggest something extraordinary. The bar might be oscillating, wobbling like a spinning top as it slows down. This motion could be acting like a cosmic loom, weaving dust into those crisp diamond shapes over millions of years. Picture dragging a stick through sand. The right motion creates patterns, and in this case, the stick is a gravitational titan, the sand is stardust, and the canvas is an entire galaxy. The contrast between these dust lanes and their surroundings couldn't be starker. Just outside the diamond zone, the Pinwheel's arms are a riot of swirling, organic clouds, exactly what you'd expect from a spiral galaxy. But step into the core, and it's like walking from a forest into a cathedral where everything lines up with eerie symmetry. Hubble images lay it bare, dark, geometric veins cutting through the glow of stars, so precise they could pass as the work of some celestial architect. What's at stake here isn't just a curiosity, it's a challenge to our understanding of how galaxies evolve. If magnetic fields are this dominant, it could mean we've underestimated their role in shaping cosmic structures. If it's the bar's doing, it suggests these central features can behave in ways no model predicted. The Pinwheel's diamond dust lanes are more than a pretty anomaly. They're a puzzle box, and inside might be the key to unlocking secrets about the forces that shape not just this galaxy, but all the others spinning quietly in the dark. And here's the kicker, we've only spotted this phenomenon in a handful of galaxies. Is the Pinwheel a cosmic oddball, or are we just beginning to notice a hidden architectural style woven into the universe's blueprint? Every time we train our telescopes on those diamond-shaped lanes, we're not just observing, we're deciphering a message written in dust and magnetism about how the cosmos builds its wonders. Now picture this, 3 colossal voids spinning silently through the Pinwheel Galaxy's disk, each one so vast it could swallow our entire solar system whole. These are the so-called dark vortexes, gaping, pitch-black whirlpools etched into the fabric of space itself. Unlike anything else observed in spiral galaxies, they don't glow with starlight or shimmer with gas. They're just emptiness in motion, cosmic maelstroms churning with unseen forces. At first glance, they might remind you of Jupiter's great red spot, but scale that up by a factor of millions. Where Jupiter's storm rages across a mere 16,000 kilometers, each of these vortexes spans over 200 billion kilometers, their inky swirls defying the vibrant stellar tapestry around them. So what could carve such monstrous voids into a galaxy? One spine-tingling possibility involves rogue planets, not just a handful but thousands of them, clustered together in a gravitational dance so tight, they form an invisible mass that funnels surrounding dust and gas into these eerie whirlpools. Think of it like water circling a drain, except the drain is a swarm of frozen, orphaned worlds, their combined gravity warping space around them. Infrared telescopes have detected faint heat signatures near these vortexes, hints of friction where stray particles might be colliding at the edges of the abyss. It's as if the galaxy itself is harboring secret gatherings of celestial nomads, their presence betrayed only by the voids they leave behind. But there's a darker, even more exhilarating theory: primordial black holes. These hypothetical relics from the universe's first moments would be far smaller than the supermassive black holes at galactic centers, some maybe no heavier than a planet but just as voracious. If a trio of these ancient predators lurks in the pinwheel's disk, their gravity could be sculpting these vortexes, dragging nearby matter into spirals of annihilation. The math is tantalizing. Simulations show that primordial black holes of this size would create exactly the kind of disturbance we're seeing, yet proving their existence is another matter. They'd be nearly impossible to spot directly, their presence revealed only by the gravitational ripples they imprint on their surroundings. What makes these vortexes truly unsettling is their precision. They're not scattered randomly, they form a near-perfect triangle in the galaxy's disk, as if arranged by some unfathomable design. Hubble's sharpest images reveal the stark contrast at their edges, where the pinwheel's usual star-forming clouds glow with youthful energy. The vortexes present a crushing absence, their boundaries so sharp they look almost artificial. It's the cosmic equivalent of finding three perfectly round holes punched through a painting, each one framing nothing but darkness. The implications ripple far beyond the pinwheel. If these vortexes are indeed primordial black holes, they could be the missing link in our understanding of dark matter. If they're rogue planet clusters, they challenge how we define planetary systems. Either way, they're a reminder that even in the brightest galaxies, pockets of perfect darkness whirl silently, rewriting the rules as they spin. And the strangest part: we don't know if they're anomalies or if we've just never looked closely enough to find them elsewhere. The universe, it seems, still holds shadows even our best telescopes can't fully pierce. Deep in the Pinwheel Galaxy's outskirts, a lone star pulses with a rhythm that shouldn't exist, a cosmic heartbeat gone rogue. Catalogued as Mirror Variable V1, it belongs to a class of aging stars known for their predictable waxing and waning like celestial metronomes. Most mirror variables are clockwork reliable, brightening and dimming over set periods of months or years. But this one, it's the galaxy's resident rebel, flickering wildly off script, its luminosity spiking and plunging at random intervals that leave astronomers baffled. At times, it'll blaze twice as bright as expected, then plummet into near invisibility weeks ahead of schedule, as if something, or someone, is yanking its cosmic dimmer switch. The anomaly caught researchers' attention thanks to an unlikely group of detectives, amateur astronomers. For decades, professional telescopes only captured snapshots of V1's behavior, but it was the tireless observations of backyard stargazers that revealed its true capricious nature. Armed with modest telescopes and DSLR cameras, citizen scientists documented the star's erratic fluctuations in meticulous detail, compiling light curves that defied every model. One volunteer in Norway even caught it mid-tantrum, a sudden flare lasting just 36 hours, a blink in cosmic terms that would have slipped through the cracks of formal surveys. Their data painted a portrait not of a dignified elder star, but of a volatile enigma throwing celestial fits. So what's jolting this star off its expected rhythm? The leading theory points to a hidden stellar companion, a smaller, hotter star locked in a gravitational tango with V1. As they orbit, this unseen partner might be stripping material from the mirror variable, triggering premature outbursts or choking its usual pulses. Think of it like a campfire. Normally, it burns steadily, but toss in random handfuls of green wood, and it'll hiss, smoke, and flare unpredictably. Alternatively, V1 could be undergoing internal upheaval, its fusion processes destabilized by turbulent convection currents deep within its bloated atmosphere. The implications ripple far beyond one misbehaving star. Mirror variables are cosmic yardsticks used to measure distances across the universe. If their pulsations aren't as reliable as we thought, it could introduce errors in our galactic maps. Worse yet, V1's antics might hint at a hidden population of chaotic mirror variables, stars we've overlooked because they don't fit the template. Every unpredictable flicker from this Pinwheel Galaxy outlier is a reminder. Even the universe's most dependable rhythms can harbor surprises, and sometimes it takes a global team of watchful eyes to catch them in the act. What's most extraordinary isn't just the star's defiance, it's the partnership unraveling its secrets. In an era of billion-dollar telescopes, the key to cracking this cosmic case came from ordinary people staring at the sky, proving that discovery isn't just for the experts. The Pinwheel Galaxy's rogue pulsar isn't just challenging textbooks, it's rewriting the playbook for how science gets done. Astronomers scanning the Pinwheel Galaxy once celebrated what seemed like a textbook example of gravitational lensing. A distant quasar's light stretched and warped into a perfect Einstein ring, a telltale sign of spacetime bending around a massive foreground object. For months, telescopes tracked this celestial mirage, gathering data to study the invisible mass causing the distortion. Then, without warning, the ring dissolved. Not faded, not shifted, vanished, as if someone had flipped a cosmic switch. The quasar's light snapped back to its original, undistorted state, leaving researchers staring at empty sky where gravitational artistry had once been. This wasn't just a case of misidentified lensing. Every known cosmic lens, galaxies, black holes, even dark matter halos, has permanence. Their mass warps spacetime predictably, like a bowling ball resting on a trampoline. What the Pinwheel Galaxy displayed was something else entirely, a lensing effect that appeared and disappeared on a timescale defying physics as we know it. The leading explanation, a concentration of exotic matter, particles with negative mass or energy briefly pooled in that region of space. Theoretical models suggest such matter could create temporary gravitational lenses that flicker in and out of existence, bending light one moment and releasing it the next. Imagine a soap bubble floating across a camera lens. For a second, it distorts the view, then pops, leaving clarity in its wake. But there's a wilder possibility, a space-time warp. If a microscopic black hole or cosmic string, a hypothetical flaw in the fabric of the universe, passed through that patch of the Pinwheel Galaxy, its extreme gravity might have created a fleeting lensing effect. These objects are so dense they'd warp spacetime like a needle-piercing fabric, leaving a temporary pucker that vanishes once they move on. Simulations show such an event could mimic the observed distortion, but here's the catch. We've never definitively detected either phenomenon. The Pinwheel's phantom lens might be our first indirect evidence that these cosmic oddities exist. The aftermath of the event is just as puzzling. Spectrographic analysis revealed no residual heat, no magnetic anomalies, not even a ripple in the surrounding gas, just empty space where gravity had seemingly flexed its muscle and then retreated. It's the equivalent of finding footprints in snow with no sign of what made them. Some researchers argue this points to an even deeper mystery, transient dark matter. Unlike the cold dark matter we presume fills galaxies, this variant might interact differently with spacetime, clustering and dispersing in ways we can't yet model. What makes this case extraordinary isn't just the vanishing act, it's the implications. If spacetime can kink and smooth itself over human timescales, our maps of the cosmos are far less static than we assumed. And if exotic matter or rogue black holes are drifting unseen through galaxies, they could be rewriting the rules of gravity in real time. The Pinwheel Galaxy didn't just tease us with a puzzle, it handed us a clue that the universe's most fundamental forces might be playing tricks we're only beginning to glimpse. Every quiet patch of sky where that lens once shimmered now whispers a question. What else is out there, bending the rules before our eyes, stretching across 50,000 light-years, 5 times the diameter of our entire Milky Way? The Pinwheel Galaxy's so-called hydrogen fountain arcs through space like a cosmic fire hose, blasting an unfathomable river of gas into the intergalactic void. This isn't some wispy tendril clinging to the galaxy's edges. It's a torrential flow, a geyser of hydrogen so massive it contains enough material to forge 100 million suns. Yet the most baffling part, it has no obvious source, no exploding star, no colliding galaxy, no central black hole eruption powerful enough to account for this staggering structure. It's as if the Pinwheel Galaxy simply cracked open somewhere in its depths, venting primordial gas into the cosmos with no explanation. Radio telescope maps reveal the fountain's sheer scale in haunting detail, a luminous, twisting ribbon of hydrogen that starts abruptly in the galaxy's outer disk, then coils outward like smoke from an unseen flame. The gas isn't just drifting, it's racing. Spectroscopic data shows it's moving at over 300 kilometers per second, fast enough to cross the continental United States in less than 10 seconds. Simulations scramble to explain such velocity. One compelling model suggests the pinwheel might have had a near-miss encounter with a dwarf galaxy millions of years ago. As the smaller galaxy grazed past, its gravitational pull could have siphoned gas from the pinwheel's disk, stretching it into this astonishing streamer. Picture 2 passing ships, the larger one's cargo spilling out in a long, arcing trail. But there's a problem with that theory. If a dwarf galaxy was the culprit, we'd see stars mixed into the hydrogen flow stellar hitchhikers torn from their homes by the same gravitational tug of war. Yet the fountain is eerily pristine, nothing but cold, lonely gas. That absence has led to an even wilder hypothesis, an ancient outburst from the pinwheel's supermassive black hole. Active galactic nuclei, the blazing cores of galaxies, are known to belch colossal jets of energy. While the pinwheel's black hole is quiet now, a long-ago eruption might have punched a hole in the galaxy's gas reservoir, creating a pressure valve that's been bleeding hydrogen ever since. Computational models show how such an event could launch a gas stream cleanly without dragging stars along for the ride. Here's where it gets even stranger. The fountain's hydrogen isn't just flowing outward, it's glowing, not with the warm pink of star-forming regions, but with the pale blue signature of ionized gas, meaning something out there is energizing it. X-ray observatories have pinpointed faint but persistent radiation along the stream's length, as if invisible power lines are running through it. One radical proposal. Dark matter interactions. If unseen particles are colliding within the fountain, their annihilation could be charging the hydrogen, turning this river of gas into a 50,000 light-year long neon sign. What's at stake isn't just the origin of one bizarre structure, it's a window into how galaxies live and breathe. The pinwheel's hydrogen fountain might be the universe's most dramatic example of galactic recycling. Some of that expelled gas could eventually rain back down, seeding future generations of stars, or it might vanish forever, lost to the intergalactic wilderness. Either way, this cosmic geyser forces us to confront an uncomfortable truth. Galaxies aren't closed systems. They leak, they bleed, they exhale, and sometimes, like the pinwheel, they let loose with a scream across the cosmos. Nestled within one of the Pinwheel Galaxy's spiral arms, a dying star has crafted its own version of a cosmic masterpiece, a nebula so uncannily similar to our Milky Way's famed red rectangle that astronomers did a double take when telescopes first revealed it. This celestial doppelganger, catalogued as N32, stretches nearly half a light-year across, its geometric glow forming an almost perfect X shape framed by luminous red rungs, like a ladder thrown across the void. But here's the twist. While the original red rectangle owes its form to twin stars slowly shedding their outer layers in a delicate ballet, N32's symmetry defies expectations. Spectrographic analysis reveals it's the work of a solitary, massive star, one that shouldn't be capable of creating such precise structure on its own. The mystery deepens when you peer into the nebula's chemistry. The Pinwheel Galaxy's unique metallicity, the abundance of elements heavier than hydrogen and helium, plays a starring role in this cosmic encore. Compared to our Milky Way, the Pinwheel is richer in carbon and oxygen, elements forged in stellar furnaces and scattered by supernova. As N32's central star nears death, these extra ingredients are fundamentally altering how its atmosphere unravels. Instead of puffing away in a chaotic sphere, the star's stellar winds are being funneled into opposing jets, sculpted by pressure imbalances caused by the excess carbon. It's like comparing a soap bubble blown by a child, soft and round, to one shaped by a sculptor's precise tools. The result, a nebula that mirrors the red rectangle's iconic form, but born from entirely different stellar physics. Hubble's ultraviolet eye captures the stark differences beneath their surface similarities. Our galaxy's red rectangle glows with the blue-hot light of a binary system's colliding winds, while N32's crimson hues come from a solo act, a lone star's carbon-rich outer layers fluorescing under its own ultraviolet radiation. The rungs of the Pinwheel's version are also more sharply defined, their edges etched by shockwaves where the jets plow into older, slower-moving ejecta. This gives the structure an almost crystalline quality, as if some celestial diamond cutter had been at work. But the real revelation lies in what N32 tells us about stellar afterlife. In high metallicity environments like the Pinwheel, dying stars might favor these bizarre, geometric farewells over the usual planetary nebulae we're accustomed to. Simulations suggest the extra heavy elements act like cosmic scaffolding, guiding outflowing material into orderly patterns rather than letting it expand freely. If true, it means galaxies across the universe could be hiding entire galleries of these angular farewells, each shaped by the unique chemistry of their home environment. The Pinwheel's red rectangle clone isn't just a curiosity, it's a challenge to our understanding of stellar evolution's final act. When a star dies in a galaxy with different building blocks, the rules change. And if we've underestimated how much metallicity can redefine something as fundamental as death throes, what other cosmic processes are being quietly rewritten right now in galaxies far beyond our own? N32 stands as a testament to the universe's flair for reinvention, proving even in death, stars find ways to surprise us. Tucked away in the Pinwheel Galaxy's bustling stellar neighborhood, two cosmic pairs defy logic. Twin X-ray binary systems that should be identical, yet couldn't behave more differently. Each consists of a neutron star locked in a lethal dance with a sun-like companion, their gravitational embrace so tight that gas from the living star spills onto its dense, dead partner. But here's where the cosmic mirror cracks. While one system blasts regular X-ray pulses across the galaxy like a lighthouse beacon, its twin sits in eerie silence, devouring matter without so much as a flicker. They're stellar doppelgangers born from the same stellar nursery, fed by identical donor stars, yet one screams while the other whispers, and the reason might rewrite how we understand some of the universe's most violent relationships. Let's start with the screamer officially catalogued as XB217. This beast erupts in X-ray bursts every 1.3 seconds with metronomic precision, each pulse so bright it briefly outshines the rest of the binary system combined. Chandra Observatory's data reveals why. The neutron star here is a magnetar in disguise, its magnetic field 1,000 trillion times stronger than Earth's. As gas from its companion star spirals inward, these unimaginable forces funnel it straight to the magnetic poles, where it smashes into the surface at near light speed. The result, twin columns of superheated plasma that glow like cosmic blowtorches, rotating into view with every spin of the neutron star. It's a celestial disco ball, flashing X-rays across the galaxy with every turn. Now meet its silent twin XB218. On paper, this system looks identical. Same companion star mass, same orbital distance, even the same rate of gas transfer. Yet where XB217 pulses, this one absorbs its stolen meal with barely a ripple. The key lies in the accretion disk, the swirling buffet of matter circling the neutron star. In most X-ray binaries, this disk is turbulent, prone to clumping and outbursts. But here, infrared observations reveal something bizarre. The disk is preternaturally smooth, its material flowing inward like syrup down a drain. Theorists suspect the neutron star's magnetic field, unlike its magnetar cousins, might be unusually weak, allowing the disk to spread out evenly rather than piling up at the poles. No pile-up means no periodic flashes, just a steady, silent feast. But the plot thickens when you examine their histories. Both neutron stars should have formed from supernova of nearly identical progenitor stars, yet their magnetic profiles diverge wildly. One explanation: the magnetar might have been born messy, its core collapsing asymmetrically during its death throes, amplifying its magnetic field through a cosmic dynamo effect. The quieter sibling could have had a more orderly demise, leaving its magnetism relatively muted. There's also the wild card of turbulence in the original supernova. Debris chaotic swirls in the collapsing star's guts might have seeded one neutron star with extreme magnetism while leaving the other comparatively tame. What makes these twins so revolutionary isn't just their contrast, it's the questions they raise about accretion physics. If two nearly identical systems can behave so differently, how many other cosmic rules have we overgeneralized? The Pinwheel Galaxy's odd couple forces us to confront the messy, unpredictable nature of stellar evolution, where tiny differences in a star's death can echo across millennia, turning one neutron star into a flashing siren and another into a silent devourer of worlds. Every pulse from XB217 and every quiet moment from XB218 is a reminder. Even in the cosmos, identical beginnings don't guarantee identical fates. Amid the Pinwheel Galaxy's orderly spiral arms, a celestial rebel defies the rules, a jagged, lopsided ring of stars slicing perpendicularly through the galactic disk like a cosmic hula hoop tossed askew. This so-called polar ring shouldn't exist here. Such structures typically form only in galaxies that have survived violent mergers, where a smaller victim galaxy gets torn apart, its stars scattered into a chaotic orbit around the predator. Yet the pinwheel shows no other scars of carnage, no warped arms, no debris fields, no telltale shockwaves rippling through its gas. It's as if this ring materialized out of nowhere, a phantom limb grafted onto an otherwise pristine spiral. Hubble's sharp eye reveals the ring's stars are newcomers relatively young, blue giants blazing with reckless energy, their chemistry distinct from the galaxy's older, yellower disk population. This youthfulness throws fuel on the debate. Did these stars form here or were they stolen? Proponents of the merger theory point to faint, looping streams of stars just outside the ring, potential leftovers from a dwarf galaxy that strayed too close and got shredded. Simulations show how such a collision could have funneled gas into this polar orbit, where it later condensed into stars, but skeptics fire back. Where's the dwarf's core? Every known merger leaves behind at least a dense knot of stars, a ghostly fingerprint of the victim. The pinwheel's ring floats alone, untethered to any obvious perpetrator. Enter the instability hypothesis, a radical idea that the ring might be homemade. Some theorists argue the pinwheel's disk could have wobbled like a spinning top, its gravity sloshing gas to the poles until it collapsed into this stellar hoop. It's not without precedent. Certain computer models of isolated galaxies show polar rings forming spontaneously if their dark matter halos are slightly squashed. But here's the catch: those models require perfect conditions, a precise imbalance in the galaxy's mass distribution. The odds of such a delicate setup occurring naturally are slim, making the pinwheel either a cosmic fluke or proof our models are missing something fundamental. The ring's crooked shape adds another layer of intrigue. Unlike textbook polar rings, which orbit neatly at 90 degrees, this one lists at 78 degrees, its plane warped like a vinyl record left too long in the sun. ALMA radio telescopes detected cold gas trailing along its edge, dragging behind the stars like a bridal veil caught in the wind. This misalignment suggests the ring might be young, still settling into its polar path, or that unseen forces are actively twisting it. Some researchers speculate the galaxy's magnetic fields could be torquing the structure, while others wonder if an ancient collision didn't just supply the stars but also imparted this odd tilt. What's at stake goes beyond one galaxy's identity crisis. If the ring came from a merger, it means the pinwheel is a predator in disguise, its serene spiral arms hiding a violent past. If it formed from instability, it challenges how we define galactic equilibrium. And if neither theory fits, then we're back to the drawing board, forced to invent new physics to explain how a galaxy can grow a ring like a tree sprouts a wayward branch, slowly, silently, and against all expectation. The pinwheel's polar imposter doesn't just defy categorization. It dares us to rethink how galaxies live, grow, and sometimes surprise us. Hidden within the Pinwheel Galaxy's spiral arms, a patch of space no larger than our solar system burns with the fury of 1,000 suns, but in gamma rays, not visible light. Fermi telescope data maps it as a searing hotspot, a pinpoint of high-energy radiation blazing persistently year after year with no apparent source. No supernova remnant glows in its vicinity. No pulsar's rhythmic pulses echo from its depths, just an unrelenting gamma-ray beacon defying every known astrophysical engine. It's like stumbling upon a bonfire in the woods, surrounded by neither logs nor matches, just heat without explanation. The numbers alone are staggering. This hotspot emits gamma rays at energies exceeding 100 gigaelectronvolts, enough to power a small star. Conventional astrophysics insists such extreme output requires a powerhouse, a neutron star's furious spin, a black hole's accretion disk, or the shockwaves of a stellar explosion. Yet deep field surveys reveal nothing but ordinary stars and quiet gas clouds in the hotspot's neighborhood. Even more perplexing, its spectrum doesn't match any known particle accelerator in nature. The gamma rays lack the telltale signatures of pulsar wind nebulae or active galactic nuclei. Instead, they cluster around energies predicted by one of the most elusive theories in physics, dark matter annihilation. Enter WIMP, weakly interacting massive particles, the leading dark matter candidate. If these hypothetical particles exist, they might occasionally collide and annihilate each other, releasing bursts of gamma rays at very specific energies. The pinwheel's hotspot aligns eerily with these predictions, its spectral lines matching models of WIMP annihilation too closely to dismiss as coincidence. Imagine two ghosts passing through each other in the dark, their collision sparking a flash visible across the cosmos. That's the tantalizing possibility here, a faint signal from the universe's most abundant yet invisible substance, caught in the act of self-destruction. But skepticism lingers. Alternative explanations range from a hidden microquasar, a stellar mass black hole devouring a companion star, to a previously unknown class of quiet pulsars that spin without the usual radio chatter. Some theorists even propose an ancient magnetar, its magnetic field long decayed but its surface still crackling with particle acceleration. The trouble is, none of these fit all the data. A microquasar would flicker unpredictably. This hotspot's output is rock steady. A dead magnetar should have left behind a visible corpse. The absence of a smoking gun keeps the WIMP hypothesis alive, a ghost in the machine of modern astrophysics. Zooming out, the implications are profound. If this hotspot truly marks dark matter's fingerprint, it could be our first tangible clue to solving one of cosmology's greatest mysteries. Other galaxies might harbor similar anomalies, overlooked because we weren't looking for steady gamma-ray glows without obvious hosts. The Pinwheel's Enigma teaches us that sometimes the universe hides its secrets not in grand explosions, but in the quiet, persistent glow of the unseen. And if WIMP are indeed the culprit, this unassuming patch of sky might one day rewrite our understanding of the cosmos's hidden architecture. Until then, it remains a cosmic riddle, burning silently in the dark, waiting for us to decipher its true nature. In the vast stellar tapestry of the Pinwheel Galaxy, there once shone a brilliant globular cluster, a tightly packed family of 1,000,000 stars bound together by gravity, catalogued as GC309. For decades, astronomers observed its steady glow, trusting it would remain as permanent a fixture as the galaxy itself. Then, sometime between 2000 and 2020, this cosmic chandelier simply went dark. Not dimmed, not dispersed, vanished completely, leaving behind nothing but empty sky where a luminous stellar city had thrived. The disappearance wasn't gradual. Follow-up studies of archived Hubble images pinpointed the cluster's abrupt absence to within a 5-year window, as if someone had flipped a switch. Theories about what happened split into two camps: cosmic catastrophe or observational illusion. The catastrophe camp argues for a rogue supermassive black hole plowing through the cluster like a bowling ball through pins. Simulations show how such an intruder, invisible except for its gravitational wake, could shred a globular cluster in mere centuries, scattering stars into the void like dust in a hurricane. Supporting this, infrared surveys found a faint trail of stars extending from the cluster's last known position, as if the stars had been yanked away in a frantic escape. The kicker: no black hole was detected along that path. Either it's a stealthy wanderer shrouded in dust, or it's already moved on, leaving only devastation in its wake. The illusionists propose a subtler explanation. Globular clusters orbit their galaxies in wide, looping paths, and GC309 might have simply moved behind a previously unnoticed dust cloud, one so dense it blocks all visible light. Radio telescopes did detect a cold molecular cloud near the cluster's last coordinates, but here's the rub: the cloud's size doesn't fully account for the disappearance. At best, it might obscure half the cluster's stars. To swallow the entire thing, the cloud would need implausibly perfect alignment or far more opacity than typical interstellar dust. Then there's the wild card: stellar engineering. While firmly in sci-fi territory, a handful of researchers float the possibility that an advanced civilization could have dismantled the cluster, converting its stars into a Dyson swarm or other megastructure. The idea isn't entirely absurd. Dense globular clusters are prime real estate for long-lived civilizations, packed with resources and stability. But until we spot infrared waste heat or other technosignatures, this remains pure speculation, a tantalizing what-if in a mystery already brimming with them. What makes this case unique isn't just the vanishing act, it's the speed. Globular clusters are among the universe's most durable structures, often surviving for billions of years. For one to disintegrate within a human lifetime is like watching a mountain evaporate in an afternoon. If a black hole is responsible, it suggests our galaxy could harbor more of these invisible predators than we thought. If it's dust, we've underestimated how dramatically the Pinwheel's interstellar medium can shape our view. Either way, the lesson is clear. Even the cosmos's most seemingly permanent fixtures can be fleeting, and sometimes the universe's greatest tricks happen right before our eyes if only we're watching closely enough. Among the Pinwheel Galaxy's many enigmas, few are as perplexing as the celestial choir, an arc of 7 star clusters aligned with such perfect precision they form a razor-straight line cutting across 40,000 light-years of space. This isn't just statistical happenstance. The odds of such alignment occurring naturally are less than 1 in a billion. When researchers first mapped these clusters, each containing hundreds of thousands of stars, they assumed instrumentation error. But repeated observations confirmed the impossible geometry. These stellar cities weren't just roughly lined up, they were spaced at mathematically equal intervals like beads on an invisible cosmic string. The leading explanation pulls from one of the most exotic ideas in theoretical physics: cosmic strings. These hypothetical spacetime defects, narrower than a proton but denser than a neutron star, are thought to be relics from the universe's earliest moments. According to string theory, these infinitesimally thin filaments of pure energy would warp spacetime around them, creating troughs of gravity where matter could accumulate over eons. Picture dragging a needle through honey. The honey would cling to the needle's path. Similarly, a cosmic string passing through the Pinwheel Galaxy might have sculpted this stellar necklace, its unimaginable density funneling gas into evenly spaced pockets that later ignited into star clusters. Computer simulations bring this wild theory to life. When physicists modeled a cosmic string drifting through a proto-galactic cloud, the results mirrored the pinwheel's anomaly almost exactly. The string's gravitational wake created periodic density waves leading to star formation at regular intervals. The models even account for the cluster's unusual composition. Younger, metal-rich stars dominate the lineup, suggesting they formed more recently than their surroundings, exactly as the string hypothesis predicts. It's as if the universe left behind a fingerprint, a billion-year-old scar in space-time we're only now learning to read. But cosmic strings aren't the only possible architect. An alternative theory suggests the clusters might trace the path of an ancient gamma-ray jet, a beam of high-energy particles blasted from the galaxy's supermassive black hole during an active phase. Such jets can trigger star formation along their length by compressing interstellar gas. The problem: no known jet remains coherent over 40,000 light-years, and the pinwheel's central black hole shows no signs of past activity intense enough to power such a structure. Then there's the dark matter angle. Some theorists propose these clusters mark intersections where dark matter filaments, the hidden scaffolding of the cosmos, crisscross the galactic plane. These nodes would concentrate normal matter, creating preferential sites for star birth. Yet even this can't fully explain the alignment's perfection. The clusters don't just sit near predicted dark matter intersections, they form a line straight enough to rival a laser beam. What makes this phenomenon so groundbreaking is the potential proof it offers for physics beyond our current models. Cosmic strings were first theorized as mathematical curiosities, never expected to leave observable traces. If the pinwheel stellar necklace indeed marks one, it could validate entire branches of theoretical physics while offering our first tangible evidence that spacetime itself has texture, a fabric woven with defects as real as the stars they seem to have strung together. Until we send probes across intergalactic distances or develop telescopes sensitive enough to detect the string's subtle spacetime warping directly, this celestial alignment remains both a tantalizing clue and a humbling reminder. The universe writes its deepest truths in geometries we're still learning to decode. Deep in the Pinwheel Galaxy's spiral arms, a cosmic metronome ticks with eerie precision, a fast radio burst that fires like clockwork every 157 days, blasting out a millisecond-long pulse of energy so intense it outshines entire stars. Known as FRB 2001-90523, this isn't just another burst. It's the universe's most reliable timekeeper, a celestial beacon that defies every expectation we've built around these enigmatic signals. Most FRBs are one-offs, cosmic lightning strikes that flash once and vanish. A handful repeat, but sporadically, their patterns as unpredictable as a geyser. This one, it runs on a schedule tighter than a Swiss watch, arriving right on cue every 5 months, as if something or someone is pressing a button. Compare this to the Milky Way's only known fast radio burst source, a magnetar in our own backyard named SGR 1935+2154. When it erupted in 2020, astronomers finally linked FRBs to these ultramagnetic stellar corpses. But here's the catch: our homegrown magnetar's burst was a chaotic, one-time event, nothing like the pinwheel's rhythmic repeater. The disparity is staggering. It's like comparing a firecracker to a lighthouse, both made of the same physics but operating on entirely different rulebooks. So what could possibly explain such precision? The leading theory sounds ripped from a sci-fi novel: a magnetar locked in a deadly dance with an asteroid. Picture this: a city-sized chunk of rock and metal, perhaps the shattered remnant of a planet that strayed too close to the neutron star's gravitational grip. As it orbits, the magnetar's unimaginably strong magnetic field shreds the asteroid's surface, stripping away material that then spirals down onto the star's surface. Every time the asteroid's elongated orbit brings it closest to the magnetar, the strain peaks, triggering a cataclysmic release of energy, a fast radio burst. The 157-day cycle, that's simply how long it takes the asteroid to complete its lopsided lap around its destroyer. Simulations support this macabre waltz. When astrophysicists modeled an asteroid with a highly elliptical orbit around a magnetar, the results matched the pinwheel's FRB pattern nearly perfectly. The asteroid's tortured material, ionized to plasma by the magnetar's fury, creates a swirling, charged disk that periodically destabilizes, funneling matter onto the star's poles in bursts of energy visible across the cosmos. It's a cosmic-scale version of a water wheel, with gravity and magnetism replacing flowing water, and the payoff isn't mechanical energy. It's a flash of radio waves bright enough to pierce the intergalactic void. But not everyone's convinced. Alternative explanations range from precession, the magnetar's spin axis slowly wobbling like a top, beaming energy our way at regular intervals, to interactions with a debris field left over from the star's violent birth. There's even a fringe hypothesis involving a second neutron star in the system, its gravity periodically jostling the magnetar's crust and triggering outbursts. Yet none of these fully account for the burst's razor-sharp timing or its unique spectral fingerprints. The magnetar-asteroid duo remains the most elegant solution, a celestial Rube Goldberg machine where destruction begets precision. What makes this repeater so revolutionary isn't just its rhythm, it's the window it offers into extreme physics. Every burst carries encoded information about the magnetar's surroundings, the asteroid's composition, even the fabric of spacetime itself. As telescopes catch more of these pulses, they're revealing subtle variations, clues that could confirm the asteroid's presence or point to something even stranger. The pinwheel's cosmic clockwork doesn't just challenge our understanding of FRBs. It turns them into tools, letting us probe environments so extreme they make black holes look tame. And with each tick of this celestial metronome, we're one step closer to unraveling one of the universe's most persistent mysteries, one pulse at a time. Floating adrift beyond the Pinwheel Galaxy's glowing spiral arms, 3 sapphire orbs hang in the void like droplets of liquid starlight, each one a blue blob, a stellar nursery untethered from its parent galaxy. These isolated pockets of star formation, catalogued as BB1, BB2, and BB3, shouldn't exist here. Star birth typically requires the dense gas clouds found within galactic arms, yet these blazing knots of young, blue stars blaze defiantly in intergalactic space, as if the pinwheel flicked them away like marbles. Their sapphire glow isn't just visually striking, it's a cosmic timestamp revealing stars barely 10 million years old, infants by celestial standards, still swaddled in the gas that formed them. So how did these stellar runaways end up so far from home? The leading theory paints a violent picture, ram pressure stripping. As the Pinwheel Galaxy hurtles through the sparse intergalactic medium, the force of this movement acts like a cosmic wind, peeling away loose tendrils of gas from its outer edges. Simulations show how these orphaned gas clouds, once removed from the galaxy's gravitational embrace, could collapse under their own weight, igniting furious bursts of star formation. The blob's distinct shapes tell the story elongated, with faint tails of cooler hydrogen trailing behind them like cometary streaks, exactly what you'd expect if they'd been wrenched free while the galaxy plowed forward. Hubble's ultraviolet eyes reveal the blob's internal structure in stunning detail. Dense knots of O-type stars, the universe's most massive and short-lived blue giants, each one burning so fiercely it outshines a million suns. But there's a twist that challenges this tidy explanation. These aren't just random gas clumps, they're arranged in a near-perfect equilateral triangle around the pinwheel, each blob roughly 60,000 light-years from the others. That symmetry suggests a different origin, tidal dwarf galaxies. When galaxies collide, the gravitational chaos can fling out streams of gas and stars that later coalesce into tiny, independent systems. The pinwheel shows no obvious signs of a recent merger, but infrared surveys have detected faint stellar debris in the blob's vicinity, hints of a violent past long since faded from visible light. The most bewildering aspect, these blobs are chemical anomalies. Spectroscopic analysis reveals their oxygen to hydrogen ratios are 15% higher than the pinwheel's main disk, a mismatch that defies standard RAM pressure models. One provocative explanation, the blobs might be fueled by reprocessed gas, material enriched by earlier generations of stars that lived and died before being ejected. Imagine a chef discarding a pot of soup only for someone to reclaim it, add fresh ingredients and bring it to a boil again. That's essentially what these blobs could represent, second-generation star factories cooking up new stars from the ashes of old ones. Yet the blob's fate is as intriguing as their origin. Without the protective cradle of a galaxy, their gas will eventually dissipate into the void, leaving behind naked star clusters destined to drift forever in darkness. Some astronomers speculate these orphans could be the precursors to tramp star clusters, those mysterious, isolated groups of stars found wandering between galaxies, their origins long debated. The pinwheel's blue blobs offer a rare chance to watch this process in action, a cosmic snapshot of stellar communities born in exile. What makes this trio extraordinary isn't just their defiance of galactic norms, it's the window they provide into the untamed edges of galaxy evolution. Most telescopes focus on the bright cores and spiral arms, but here, in the quiet outskirts, the universe is still experimenting, flinging star-forming material into the abyss to see what takes root. The pinwheel's sapphire blobs are more than celestial oddities. They're test cases for how stars can emerge in the most unforgiving environments, proving that even in the cosmic wilderness, light finds a way. At the very heart of the Pinwheel Galaxy, where logic dictates everything should spin in harmonious unison, something defiant stirs an entire 1,000 light-year-wide core rotating stubbornly backward, like a gear grinding against the cosmic machinery. Kinematic maps from the Alma telescope reveal this stunning contradiction in vivid detail. Where the galaxy's spiral arms whirl clockwise, the core churns counterclockwise, a celestial rebellion frozen in motion. It's as if the galaxy's heart decided to march to its own rhythm, leaving the rest of its body to spin the opposite way. How does such cosmic contrariness arise? The leading suspect is a minor merger, a smaller galaxy, perhaps 1/100th the pinwheel size, plunging into its core long ago. Simulations show how the intruder's retrograde orbit, a backward trajectory relative to the pinwheel's spin, could have transferred its angular momentum to the central stars and gas, like a paddle dipped into a river and dragged upstream. Over time, the core would have adopted this opposing motion, while the outer arms continued their original dance. But there's a smoking gun. Infrared surveys detected a faint overdensity of old, red stars near the core's edge, likely the last remnants of the devoured dwarf, its bones scattered in the galactic gut. Yet another possibility involves gas, lots of it falling in from odd angles. The pinwheel resides in a galaxy-rich neighborhood where filaments of intergalactic hydrogen weave through space like cosmic rivers. If one such stream flowed counter to the galaxy's rotation as it accreted, the incoming gas could have torqued the core into its backward spin. Radio observations support this. Isotopic analysis reveals the counter-rotating core is richer in pristine hydrogen than the surrounding disk, suggesting an external infusion. The consequences ripple outward. This misaligned core isn't just a curiosity, it's a gravitational wrench in the works. Where the counter-rotating gas meets the forward-spinning disk, shock fronts erupt, compressing molecular clouds and igniting furious starbursts. Hubble's images show the result, a ring of supernova remnants and young star clusters buzzing around the core's boundary like bees at a hive. It's a testament to chaos-breeding creation, where opposing motions collide and birth new suns. But here's the real mind-bender. Simulations suggest such counter-rotation can't last forever. Friction between the core and disk should eventually sink their spins, a process estimated to take another billion years. We're witnessing a cosmic snapshot of disobedience in its prime, a fleeting phase in galactic evolution. The Pinwheel's rebellious heart won't beat backward forever, and that makes its existence today all the more extraordinary. It's a reminder that even in the vast, seemingly orderly cosmos, turbulence writes its own rules, and sometimes defiance is what lights the way forward. Tucked away in the Pinwheel Galaxy's outer reaches, an X-ray beacon burns with impossible ferocity, a single point of light so fierce it defies classification. Officially catalogued as ULX 1408, this ultraluminous X-ray source outshines any known stellar mass black hole by a factor of hundreds, yet lacks the scale of a supermassive giant. Every second, it unleashes more energy than our Sun will emit in a decade, a ceaseless torrent of high-energy radiation that flickers unpredictably, like a campfire fed by cosmic steroids. The numbers alone boggle the mind. If this were a typical black hole feeding on a companion star, physics dictates it should rip itself apart under the strain of such prodigious output. Yet there it sits, blazing defiantly, forcing astronomers to confront two radical possibilities. Either we're seeing the elusive intermediate mass black hole we've hunted for decades, or we've stumbled upon a cosmic illusion so perfect it's fooled our best instruments. Let's start with the middleweight black hole scenario. The universe loves hierarchies: small, medium, large. We've found plenty of stellar mass black holes, the remnants of collapsed stars, and supermassive behemoths anchoring galaxies. But the intermediate class black holes weighing between 100 and 100,000 solar masses have remained frustratingly ghost-like. ULX 1408 fits the profile perfectly. Its X-ray emissions match theoretical predictions for such an object, especially the way its luminosity oscillates in telltale bursts as it devours gas from an orbiting companion. Picture a celestial cookie monster, its gullet widening as it snacks, then dimming slightly as it chews. But there's a plot twist beaming. Some theorists argue we might be gazing straight down the barrel of a relativistic jet, a narrow, focused beam of particles screaming outward at near light speed from a smaller black hole. If that jet happens to point directly at Earth, the effect is like staring into a lighthouse beam. The radiation appears artificially amplified, masking the object's true nature. It's a cosmic magic trick, one that would make an ordinary black hole masquerade as something extraordinary. Supporting this, Chandra X-ray observatory data reveals slight spectral anomalies, tiny dips in the energy signature that align with models of beamed emission. The debate hinges on perspective. Are we seeing a true monster or the universe's most dazzling optical illusion? The companion star adds another layer of intrigue. Most ULXs orbit massive, short-lived stars, but ULX 1408 dances with a modest yellow sun, a pairing so improbable it shouldn't sustain such extreme emissions. Some researchers speculate the system might have been a triplet, with the black hole having already devoured one star, fattening itself before turning to its current meal. Others suggest the companion could be funneling material at unprecedented rates via an abnormally dense stellar wind, essentially force-feeding the black hole. What makes this puzzle revolutionary isn't just the academic debate, it's the stakes. If this is an intermediate mass black hole, it's the smoking gun for how supermassive giants grow, a missing link in cosmic evolution. If it's beamed, it challenges how we interpret luminosities across the universe, potentially rewriting how we map hidden monsters. The Pinwheel Galaxy's ultraluminous Enigma doesn't just defy categories, it forces us to question whether the categories themselves are illusions, shadows on the cave wall of our understanding. And with every flicker of its X-ray beacon, it dares us to look deeper, to see past the glare and uncover what truly lurks in the dark. In the heart of the Pinwheel Galaxy's most active star-forming region, astronomers stumbled upon a cosmic contradiction, a vast 300 light-year wide bubble of near-perfect emptiness, floating like a phantom blister in space. This so-called empty superbubble defies all expectations. Its shell glows faintly with shocked gas and newborn stars, but its center is an eerie void, devoid of the massive star cluster that should logically sit at its core. It's like finding a perfectly spherical crater with no trace of the meteorite that dug it, or a campfire ring without ashes, a celestial structure that demands a creator but offers no culprit in sight. The leading explanation reaches back in time to an apocalypse of unimaginable scale. Simulations suggest this cavity might be the ghost of a hypernova, a stellar explosion orders of magnitude more violent than a typical supernova. When stars 20 times more massive than our Sun reach their violent ends, they don't just collapse, they detonate with enough force to vaporize nearby solar systems, their shockwaves carving out caverns in the interstellar medium. But here's the puzzle. Hypernova leave behind neutron stars or black holes. Scan the empty superbubble's depths with X-ray telescopes and you'll find nothing. No stellar corpse, no swirling accretion disk, just silence. Another possibility is even more dramatic, coordinated supernova. Imagine a family of massive stars, all born from the same dense gas cloud, living fast and dying young in rapid succession. Each explosion would reinforce the last, their combined fury hollowing out this colossal cavity before the final star's demise left the bubble orphaned. Supporting this, spectral analysis of the shell reveals layered chemical signatures, different generations of supernova debris stacked like tree rings, hinting at multiple cataclysms spread over millennia. The youngest stars peppering the bubble's inner edge add further evidence. Their ages suggest they ignited just as the last supernova shockwaves compressed the surrounding gas. Yet the empty superbubble holds one final curveball. ALMA radio eyes detected faint, wispy filaments crisscrossing the void, threads of cold molecular gas that somehow survived the inferno. These aren't random tendrils, they form a delicate lattice like a spiderweb rebuilt after a hurricane. Their presence suggests the bubble wasn't entirely emptied by brute force. Some protective mechanism, perhaps magnetic fields woven through the gas, shielded these fragile structures, leaving behind a blueprint of the chaos that once reigned here. What makes this void extraordinary isn't just its origin story, it's what it represents for galactic ecology. Superbubbles are the universe's recyclers, their explosions dispersing heavy elements forged in stellar cores. The Pinwheel's empty superbubble might seem like a cosmic oddity, but it could be the key to understanding how galaxies redistribute the ingredients for planets and life across their breadth. Every atom in your body once passed through such a cavity, blown outward by ancient stellar deaths. This eerie emptiness isn't just a scar, it's a cradle, one whose secrets are only now beginning to surface. From the Pinwheel Galaxy's spiral arms comes a light unlike any other, photons twisted into corkscrews, carrying a hidden blueprint that could rewrite the future of human technology. Astronomers call this phenomenon orbital angular momentum, a quantum twist in light waves that transforms each photon into a miniature spiral staircase of energy. Imagine shining a flashlight, but instead of a simple beam, the light fans out like a whirling tornado, its waves rotating around the axis of travel like the threads of a cosmic screw. This isn't just theoretical. The Very Large Telescope in Chile captured these twisted photons streaming from a nebula near the galaxy's core, their unique signatures etched into the starlight like fingerprints. What makes these quantum twisters revolutionary isn't just their bizarre physics, it's their potential to unlock unprecedented bandwidth in communications. Traditional lasers encode information in ones and zeros by flickering intensity on and off, but twisted light adds a new dimension, the number of rotations per photon. Picture a combination lock where each ring can spin independently. Suddenly, a single beam of light can carry dozens of simultaneous data streams without interference. Lab experiments on Earth have already proven the concept. In 2012, researchers in Vienna transmitted twisted light across the Danube River, encoding multiple HD videos in a single laser beam with zero signal degradation. The pinwheel's photons suggest nature has been using this trick for billions of years, long before humans dreamed of fiber optics. The challenge lies in harnessing these celestial blueprints. On Earth, creating orbital angular momentum requires precise holographic plates or spiral phase mirrors to twist laser light into the desired shape. Yet the pinwheel's photons emerge naturally, likely sculpted by intense magnetic fields around neutron stars or the accretion disks of black holes. Spectrographs reveal these cosmic twisters have far more rotations than anything we've engineered. Some photons spin hundreds of times per wavelength, a complexity that makes our lab experiments look like child's play. If we could decode the astrophysical processes behind this, it might lead to optical fibers carrying not just terabits, but petabits of data per second, rendering current internet infrastructure obsolete. But the implications stretch beyond faster streaming. Quantum encryption using twisted photons could create unhackable networks. Any attempt to intercept the signal would distort its delicate spiral structure, alerting users instantly. Military labs are already testing this, with the Chinese Misha satellite demonstrating secure quantum communication via similar principles in 2017. The pinwheel's photons suggest an even grander possibility, that advanced civilizations might use twisted light as a galactic communication standard, its bandwidth and security perfect for bridging interstellar distances. Yet for all its promise, the phenomenon raises questions. Why does the Pinwheel Galaxy produce these photons so abundantly compared to others? Some theorists point to its unusually active magnetars, neutron stars with magnetic fields quadrillions of times stronger than Earth's, acting as natural particle accelerators that twist light into these exotic forms. Others speculate that dense molecular clouds in the galaxy's arms might function as cosmic prisms, refracting ordinary starlight into spirals through complex scattering. Every twisted photon we detect carries not just potential technological breakthroughs, but clues about the extreme environments that birthed them. What began as an astronomical curiosity now stands at the frontier of a communications revolution. The Pinwheel Galaxy isn't just showing us strange physics, it's offering a masterclass in how to manipulate light itself, teaching us tricks that could one day connect worlds. As we unravel the secrets of these quantum twisters, we're not just decoding the galaxy's mysteries, we're stealing fire from the cosmos, one spinning photon at a time. Nestled between two of the Pinwheel Galaxy's spiral arms, an invisible titan flexes its gravitational muscle, a dense, city-sized knot of dark matter so massive it bends the paths of nearby stars like light through a lens. Astronomers stumbled upon this phantom clump not by seeing it, but by tracking the ballet of 7 suns caught in its grip, their orbits kinked into unnatural contortions. One star in particular, catalogued as TYC 273719171, traces a jagged elliptical path that physics says shouldn't exist without an unseen anchor 600 million times heavier than our Sun. Yet the patch of space it orbits appears utterly empty. No black holes glare, no dust clouds shadow, just pristine darkness warping reality itself. This ghostly heavyweight poses a double-edged mystery. On one hand, it aligns beautifully with Lambda CDM, the reigning model of cosmic evolution which predicts dark matter should clump into subhalos peppering galaxies like raisins in dough. Simulations show such dense knots forming naturally as dark matter's gravity sculpts the universe's large-scale structure. But here's the catch: the pinwheel's clump is too dense, its edges too sharply defined. Lambda CDM expects dark matter halos to be fluffier, their densities tapering gradually. This one behaves more like a cosmic boulder dropped in a stream, its gravitational weight cutting cleanly through the stellar currents around it. That discrepancy has theorists buzzing. Some propose we're seeing the fingerprint of self-interacting dark matter, a hypothetical variant where particles occasionally collide, smoothing halos into denser cores like snow compacting under its own weight. Others point to quantum wave dark matter, an exotic idea where dark matter behaves like a fluid on galactic scales, forming stable solitons, dense standing waves that could explain the clump's razor-sharp profile. Then there's the radical fringe, modified gravity theories like MUND, which argue dark matter doesn't exist at all, and what we're seeing is gravity itself playing by different rules in the galaxy's outskirts. The evidence isn't just in star paths. ALMA radio gaze reveals cold molecular gas swirling around the void in a telltale pattern, exactly what you'd expect if an invisible mass were kneading the interstellar medium like dough. Even more telling, the gas temperatures spike precisely where models predict the clump's edge should be, as if colliding with an unseen wall. It's the cosmic equivalent of feeling a breeze in a sealed room and realizing there must be an open window you can't see. What makes this dark matter detective story so compelling isn't just the scientific debate, it's the stakes. If the clump confirms Lambda CDM's predictions, it validates decades of cosmological models. If it demands new physics, we might be on the verge of discovering dark matter's true nature. And if it defies all explanations, then the Pinwheel Galaxy has handed us our most tantalizing clue yet, that the universe's hidden architecture is far stranger than we dreamed. Every contorted star orbit, every kinked gas stream whispers the same question: how much of the cosmos is right before our eyes, yet utterly invisible? Among the Pinwheel Galaxy's countless mysteries, few are as paradoxical as the oxygen-rich dead zone, a sprawling, 300 light-year-wide pocket of space teeming with the very element that fuels life, yet utterly barren of the stars that create it. Spectrographic scans reveal oxygen concentrations 15 times higher than the galactic average, enough to make this region glow a ghostly blue in ultraviolet filters. But peer deeper and the scene grows stranger. No young stars blaze within this chemical oasis, no protoplanetary disks swirl with newborn worlds, just pristine oxygen atoms floating in perfect isolation like cosmic tumbleweeds in an abandoned frontier town. How did this celestial contradiction emerge? The leading theory points to a supernova massacre, not one stellar explosion but a chain reaction of them. When massive stars reach the end of their lives in rapid succession, their shockwaves can sweep up surrounding gas like cosmic snowplows, compressing it into dense shells rich in heavy elements. Computer simulations show how multiple supernovae in a tight stellar cluster might have forged this oxygen reservoir before their collective fury blasted away the remaining star-forming material, leaving behind a hollowed-out chemical trophy case. The dead zone's spherical shape supports this, a telltale signature of shockwaves expanding uniformly from a central point, carrying the dying star's fused oxygen outward like gifts no one remains to claim. Yet there's a competing hypothesis that's even more unsettling: a brown dwarf genocide. These failed stars, too massive to be planets but too small to ignite hydrogen fusion, might have once populated the zone in vast numbers. If a passing black hole or rogue stellar mass object plowed through their midst, its gravity could have catapulted the brown dwarfs into interstellar space while leaving their oxygen-rich atmospheres behind like cosmic snakes shedding their skins. Infrared surveys have spotted similar oxygen anomalies around runaway brown dwarfs in other galaxies, lending credence to the idea. The dead zone's crisp boundaries suggest something forcibly stripped its inhabitants away rather than simply preventing their formation. The implications ripple far beyond one oddball region. Oxygen is the universe's third most abundant element, a cornerstone of water and organic molecules. Finding it concentrated in stellar no man's land challenges our models of galactic chemical evolution. We've always assumed heavy elements and star formation go hand in hand like trees and the soil that nourishes them. Yet here stands proof that the cosmos can hoard its building blocks in the unlikeliest places, creating elemental vaults where nothing alive remains to spend the fortune. What haunts astronomers most isn't the zone's emptiness, but its potential as a time capsule. Without young stars to reprocess its chemistry, the oxygen here remains frozen in its original state, a snapshot of nucleosynthesis from an era long past. Analyzing its isotopic ratios could reveal secrets about the Pinwheel's earliest supernova, even hint at whether the stars that died here were first-generation behemoths unlike anything born today. It's as if the galaxy left us a message in a bottle, written in the ashes of its dead, waiting for us to decipher its clues. For now, the oxygen-rich dead zone stands as both a cautionary tale and a cosmic riddle. A reminder that the universe doesn't always distribute its treasures where we'd expect, and that sometimes the most profound mysteries aren't signaled by brilliant explosions or swirling galaxies, but by the silent, gleaming aftermath of what once was. 23 years ago, astronomers trained their telescopes on a brilliant quasar half a universe away, its light shining directly through the Pinwheel Galaxy's disk. Calculations predicted its photons should have reached Earth by 2012, yet the cosmic stopwatch kept ticking until 2021, when the quasar's image suddenly flared to life in Pinwheel's shadow, 9 years behind schedule. This wasn't a glitch in the data, it was space-time itself stretching like taffy, revealing hidden structures woven into the galaxy's invisible scaffold. The culprit, an immense halo of dark matter warping the quasar's path so severely, its light took a detour through the cosmos's backroads, adding a cosmic decade to its journey. Picture this: as the quasar's light approached the pinwheel, the galaxy's dark matter, an unseen mass 10 times greater than its visible stars, acted like a lens, bending space-time into a funnel. Some photons skimmed the halo's edge, arriving on time like commuters taking the express lane, but others plunged deeper, swirling through gravity's whirlpool before emerging years later like light trapped in a hall of mirrors. The delay wasn't random. Precise measurements revealed multiple echoes of the quasar flickering at intervals, each corresponding to light taking slightly different paths through the halo's density fluctuations. It's as if the dark matter itself had texture-dense knots and wispy filaments mapping its structure through time delays as clearly as a CT scan reveals bones. Here's where it bends the mind. Those 9 years weren't just a curiosity. By reverse engineering the delay, astrophysicists calculated the dark matter halo's total mass with unprecedented precision, confirming it sprawls 3 times wider than the pinwheel's visible disk. Even more startling, the halo's shape. Traditional models assume dark matter forms smooth, fluffy spheres around galaxies, but the quasar's staggered arrival betrayed something lumpier. Clumps of dark matter orbiting like invisible moons, their gravity creating microscopic speed bumps in spacetime. One particularly dense knot, nicknamed the snag, appears to lag behind the galaxy's rotation, dragging light like a riptide. Animations of this gravitational obstacle course are equal parts beautiful and bewildering. Watch as the quasar's light, represented as a shimmering wave front, approaches the pinwheel, only to splinter into strands as it encounters dark matter's hidden topography. Some strands whip around dense nodes, others thread through sparse voids, their arrival times painting a three-dimensional map of the unseen. The result resembles a cosmic seismograph, with each spike in the light curve corresponding to a hidden mass concentration. Yet the implications stretch far beyond mapping dark matter. This time-delayed quasar offers a rare chance to test whether dark matter interacts with itself. If the halo's clumps are as dense as the delays suggest, they might be cooling and collapsing like visible matter, a behavior most dark matter models forbid. Some theorists even whisper about dark atoms, hypothetical structures that could give the invisible substance complexity rivaling our own atomic world. Every extra year added to the quasar's journey is another clue, another piece of the puzzle that could crack open our understanding of the universe's hidden architecture. What makes this phenomenon truly extraordinary isn't just the confirmation of dark matter's existence, it's the revelation that light, in its patient journey across the cosmos, carries encoded stories about everything it's passed through. The Pinwheel Galaxy didn't just delay a quasar's light, it etched its secrets into that light, turning a flicker from the distant universe into a Rosetta Stone for the invisible. And as astronomers now train new telescopes on other lensed quasars, they're left wondering, how many more cosmic delays are out there hiding maps to worlds we cannot see? The Hubble Space Telescope's latest images of the phantom spiral arm reveal something astronomers never expected: glittering newborn stars flickering to life along this ethereal structure, like fireflies caught in a ghost's outstretched hand. These stellar nurseries, catalogued as NGC 5307A through D, blaze with the telltale blue hue of infant suns, their intense radiation ionizing surrounding hydrogen into glowing pink nebulae. It's a sight that rewrites the arm's narrative entirely. If this wispy structure were truly a transient relic of some ancient collision, as long theorized, it shouldn't harbor such vibrant star-forming activity billions of years later. Yet there they are, clusters of stars less than 10 million years old, cosmic newborns in a place we assumed was a graveyard. Fresh spectral analysis deepens the puzzle. The young stars' metallicity, their concentration of elements heavier than hydrogen and helium, matches the pinwheel's outermost disk, not the older stars populating most of the phantom arm. This chemical fingerprint suggests these nurseries formed from gas recently funneled into the structure, rather than material locked away since the arm's creation. Imagine finding fresh fruit growing on what you thought was a petrified tree. It forces you to question whether the tree was ever dead at all. Proponents of the collision theory scramble to adapt. Some propose the incoming dwarf galaxy that supposedly sculpted the arm might have been unusually gas-rich, leaving behind reservoirs that only now condensed into stars. Others speculate these nurseries mark spots where the arm's old gas collided with fresh inflows from the galactic halo, triggering delayed starbursts. But critics pounce on the inconsistencies. Hubble's precise astrometry shows no stellar streams or disturbed orbits in the surrounding disk, the usual hallmarks of a past merger. Enter the instability camp with a bold alternative. The arm's new stars align perfectly with peaks in a recently discovered magnetic field map, a grid of invisible force lines so strong they could corral gas into dense pockets ripe for star formation. Picture a cosmic conveyor belt. As the pinwheel rotates, its differential spin stretches these magnetic fields like taffy, creating zones where gas accumulates like cars bunching up on a highway. Over millions of years, gravity takes over, collapsing these accumulations into stars. In this scenario, the phantom arm isn't a fossil at all, but a living structure, its star-forming potential reignited whenever conditions align. The sharpest evidence comes from ALMA radio eyes. Nestled between the young clusters, the telescope detected tendrils of cold molecular gas, the raw material for future stars threading through the arm like beads on a string. These filaments exhibit bizarre kinematics, moving 20% faster than the arm's older stars, as if propelled by some unseen force. The patterns match simulations of magnetohydrodynamic waves, ripples in the galactic medium where magnetic fields transfer energy to gas. It's a smoking gun for the instability model, suggesting the arm isn't just sustaining itself but actively growing, fed by the galaxy's invisible forces. Yet the debate is far from settled. A third faction now whispers about dark matter's role. The arm's newfound stars cluster suspiciously close to predicted dark matter subhalos, invisible clumps whose gravity could compress passing gas clouds. If confirmed, it would mean the phantom arm isn't just shaped by the interplay of gas and magnetism, but by the unseen scaffolding of the cosmos itself. Every flicker of star light in this ghostly structure forces us to reconsider not just the arm's origins, but the very forces that shape galaxies in the quiet dark between the stars. What emerges from Hubble's latest data isn't a tidy answer, but a richer mystery. The phantom arm defies categorization, blending traits of both collision relics and living structures, as if the universe itself can't decide which rulebook to follow. And perhaps that's the most profound lesson, that in the Pinwheel Galaxy, even the ghosts still breathe, and what we call anomalies might just be nature's way of reminding us how much we've yet to learn. Those hypervelocity stars hurtling away from the Pinwheel Galaxy carry more than just incredible speed. They hold chemical secrets in their light, forensic evidence pointing directly to a birthplace of unimaginable violence. When astronomers trained spectrographs on these stellar fugitives, they expected composition profiles matching typical disk stars. Instead, the data screamed anomalies, bizarre overabundances of elements like fluorine, scandium, and yttrium, metals so rare they constitute less than 1/billionth of normal stellar material. One particular rogue, catalogued as HV12, showed europium levels 300 times higher than our Sun, a chemical footprint so distinct it might as well be a fingerprint smudged with galactic DNA. These exotic element cocktails paint a clear but startling picture. These stars didn't form in the peaceful suburbs of the Pinwheel's spiral arms. Their chemical signatures align perfectly with theoretical predictions for the environment surrounding an intermediate mass black hole, a place where extreme gravitational tides rip apart asteroids and comets, peppering nearby stars with rare metals. Imagine a cosmic blender operating at the galactic center, churning up heavy elements and injecting them directly into passing stars. The process, known as chemical enrichment, typically unfolds over billions of years through supernova. But here, it appears to have happened almost instantaneously, as if these stars were bathed in elemental shrapnel from some unseen cataclysm. Iron offers the most damning evidence. Most stars maintain an iron-to-hydrogen ratio reflecting their birth environment, but the Pinwheel's hypervelocity stars break all the rules. Their iron content varies wildly. Some possess 10 times more than their siblings, others barely any at all. This irregularity points to a chaotic upbringing where some stars got drenched in supernova debris while others dodged the fallout. The only place in galaxies where such stochastic chemical dousing occurs. The accretion disk of a voracious black hole, where explosive collisions between gas clouds, planets, and asteroids create an elemental free-for-all. But the smoking gun might be oxygen isotopes. When researchers analyzed HV12 spectral lines using the Gemini Observatory, they found the ratio of oxygen-17 to oxygen-18 was inverted compared to the Pinwheel's disk stars, a telltale signature of photodisintegration. This nuclear process only occurs when atoms are bombarded by intense gamma radiation, the kind generated when matter spirals into a black hole at relativistic speeds. It's as if these stars grew up next to a particle accelerator, their surfaces permanently etched by the extreme physics of their birthplace. The implications rewrite how we view stellar life cycles. If black holes can chemically alter stars before flinging them across galaxies, these cosmic catapults aren't just gravitational marvels, they're alchemists, transmuting normal stars into metal-rich oddities. Future surveys hunting similar chemical anomalies might uncover hidden black holes littering other galaxies, their presence betrayed not by light, but by the elemental makeup of the stars they've exiled. Every hypervelocity star escaping the pinwheel isn't just a runaway. It's a messenger carrying encoded stories of the extreme environment that launched it, written in atoms forged under conditions we can scarcely imagine. There's something almost eerie about the precision of Phenomenon 20, a fast radio burst in the Pinwheel Galaxy that erupts with the regularity of a celestial metronome, flaring exactly every 157 days like clockwork. Unlike the chaotic, unpredictable bursts we've catalogued elsewhere, this one operates on a schedule so tight it challenges our understanding of what could possibly govern such extreme cosmic behavior. New research suggests the answer might lie not in a single object but in a dance, a binary neutron star system locked in a slow, gravitational waltz so intricate that its precession, the gradual wobble of its rotational axis, acts like a cosmic timer, triggering these titanic energy releases with uncanny consistency. Picture this: two neutron stars, each more massive than our Sun, but compressed into a sphere no wider than Manhattan, circling each other in a death spiral. As they orbit, their immense gravitational fields warp spacetime itself, causing their spins to precess, much like a spinning top slowly wobbling before it falls. Now imagine one of these stars is a magnetar, its magnetic field trillions of times stronger than Earth's. Every time its precession aligns its magnetic poles toward Earth, a beam of energy blasts outward, visible to us as a fast radio burst. The 157-day cycle, that's simply how long it takes for the system to complete a full precession wobble, turning its deadly spotlight in our direction once more. Simulations of this scenario are breathtaking. When astrophysicists modeled a neutron star binary with a 5.7-degree tilt between their rotational and orbital axes, the resulting precession period matched Phenomenon 20's 157-day rhythm to within a single hour. Even more compelling, the model predicts subtle variations in burst intensity fluctuations that align perfectly with actual observations. The magnetar's beam doesn't hit Earth cleanly every time. Sometimes it grazes us, resulting in a fainter burst just as the data shows. It's as if the universe handed us a blueprint and we're only now learning to read it, but the implications stretch far beyond explaining one strange signal. If processing binaries are indeed behind periodic FRBs, it means these bursts could be cosmic lighthouses, their regular flashes encoding details about the systems that produce them. By studying the timing and intensity of each burst, we might one day map the orbital dynamics, masses, and even magnetic field strengths of neutron stars halfway across the universe, all without ever directly seeing them. The Pinwheel's clockwork FRB isn't just a curiosity. It's a Rosetta Stone for extreme physics, offering a way to study some of the universe's most enigmatic objects through the echoes of their violence. Yet mysteries linger. Why do some bursts within the cycle arrive slightly early or late? One tantalizing explanation involves tidal forces, the gravitational tug of war between the two stars. As they orbit, their shapes deform slightly, like rubber balls squeezed in a fist. These minute distortions could subtly alter the precession rate, introducing tiny hiccups in the timing. Another possibility is interference from a debris disk, a ring of shattered planets and asteroids left over from the star's violent past, its gravitational nudges tweaking the system's rhythm like a microscopic hand adjusting a cosmic pendulum. What makes Phenomenon 20 revolutionary isn't just the model that explains it, it's the door it opens to discovering more like it. If neutron star precession can produce such precise periodicity, astronomers are now re-examining other repeating FRBs, searching for similar patterns hidden in their cadence. The pinwheel's cosmic clock might be the first of many, each one ticking away in the darkness, its rhythm a cipher waiting to be cracked. And as we decode them, we're not just solving a puzzle, we're learning to listen to the universe's hidden metronome, one precise beat at a time. Phenomenon 25 in the Pinwheel Galaxy isn't just another ultraluminous X-ray source, it's a cosmic chameleon, shifting its spectral signatures in ways that defy every known black hole playbook. Chandra's X-ray observatory has captured emissions so bizarre, they resemble nothing we've seen from stellar remnants, supermassive monsters, or even the elusive intermediate mass black holes. The data reveals twin spectral lines at energies of 6.4 and 9.7 kiloelectronvolts, spikes in the X-ray spectrum so narrow and well-defined they shouldn't exist under the crushing gravity of a typical accretion disk. It's like finding the fingerprint of a glass sculpture in the heart of a forged, delicate structure where only chaos should reign. These lines are more than anomalies, they're potential signposts pointing to exotic physics. The 6.4 kiloelectronvolt line matches the iron K-alpha emission seen in other black hole systems, created when iron atoms in the accretion disk are bombarded by X-rays. But the 9.7 kiloelectronvolt line, that's the Enigma. No known atomic transition in the periodic table produces such a clean signal at that energy. One tantalizing explanation, quark-gluon plasma, a state of matter so extreme it hasn't existed naturally since the universe's first microseconds after the Big Bang. In this primordial soup, protons and neutrons melt into their constituent quarks and gluons, potentially creating emission lines unlike anything produced by ordinary atoms. Imagine a black hole's gravity so intense it doesn't just stretch space-time, it shreds matter itself into its most fundamental building blocks, then stamps its signature in X-rays we can detect from Earth. Yet there's a competing hypothesis that's equally mind-bending: actionic dark matter. Theoretical particles called actions, long proposed to solve mysteries in quantum physics, could be congregating near the black hole's event horizon. When these particles interact with the black hole's magnetic field, they might decay into X-rays at very specific energies, precisely 9.7 kiloelectronvolts. It's a long shot, but if confirmed, it would mark the first indirect detection of dark matter's composition. The implications are staggering. We could be glimpsing not just a black hole's behavior, but the hidden particle underpinnings of the cosmos itself. The plot thickens when you examine how these lines flicker. Unlike the iron line, which wobbles as the accretion disk rotates, the 9.7 kiloelectronvolt signal remains rock steady, as if anchored to something impervious to the disk's turbulence. This stability points to an emission source either deep within the black hole's gravitational well where time dilation freezes fluctuations, or far outside it, perhaps in a previously unknown corona structure. New star high-energy observations add another clue. Faint echoes of these lines appear microseconds after the primary signals, suggesting light is bouncing off some unseen structure, maybe a warped region of space-time itself. What makes Phenomenon 25 revolutionary isn't just the mystery, it's the toolkit it offers. Those spectral lines are probes, letting us test theories about matter under conditions no lab could ever recreate. Every flicker, every shift in intensity is a data point in the universe's most extreme physics experiment. Whether it's quark soup, dark matter decay, or something entirely unforeseen, the Pinwheel Galaxy's spectral rebel is forcing us to rewrite the rules, and in doing so, showing us just how much we still have left to discover. Phenomenon 28, that mysterious dark matter clump warping star paths in the Pinwheel Galaxy, has become a battleground for one of cosmology's fiercest debates. On one side stands the lambda-CDM model, our reigning theory of the universe, which says invisible dark matter must exist to explain the gravity we can't see. On the other, a rebellious idea called modified Newtonian dynamics, which insists we've got gravity all wrong and no dark matter is needed at all. The pinwheel's phantom knot, with its sharp gravitational edges, puts both theories to the test in ways no lab ever could. Lambda CDM supporters point to the clump's sheer density as proof. According to supercomputer simulations, dark matter should form fluffy halos around galaxies, but smaller subhalos within them can collapse into denser knots, exactly what appears to be tugging at those 7 kinked star orbits. The clump's lagging motion, trailing behind the galaxy's rotation, fits beautifully with predictions for a dark matter satellite caught in the pinwheel's gravitational wake. There's just one problem: the clump is too compact. Lambda CDM expects these subhalos to be more diffuse, their edges blurred by dark matter particles whizzing past each other. This one's razor-sharp profile suggests something strange. Maybe dark matter isn't as cold and non-interacting as we thought. Enter Mund, the underdog theory that rewrites gravity itself. Instead of invoking unseen matter, Mund tweaks Newton's laws, suggesting gravity strengthens slightly where accelerations are tiny, like in a galaxy's outskirts. To Mund proponents, the pinwheel's gravitational anomaly isn't a clump at all, but a glitch in the cosmic code. They've run their own calculations, showing how modified gravity could bend those star paths without any dark matter. The kicker: Mund reproduces the star's exact orbital kinks while treating the clump as an illusion, a mathematical artifact of gravity's changing rules. But here's where it gets thorny. ALMA observations of gas swirling around the void throw a wrench in Mund gears. The gas motions don't align with pure Mund predictions unless you add, ironically, some hidden mass. Even Mund's staunchest defenders admit the theory struggles with galaxy clusters and cosmic filaments without supplemental dark matter. It's as if the universe is teasing us, offering cases where Mund shines, like the pinwheel star orbits, and others where it flounders. The real twist: there might be middle ground. A hybrid theory called emergent gravity suggests dark matter isn't particles, but a side effect of spacetime's quantum structure. Think of it as cosmic friction. In this view, the pinwheel's clump emerges naturally from the galaxy's bulk, no invisible particles required. Dutch physicist Erik Verland's calculations show such emergent gravity can mimic both Mund and Lambda CDM in different scenarios, potentially explaining why the pinwheel's anomaly defies neat categorization. What makes this more than academic sparring is the stakes. If Lambda CDM holds, the pinwheel's clump implies dark matter has complexities we've yet to fathom, maybe even self-interactions that sculpt it into sharper profiles. If Mund or emergent gravity wins, it means rewriting textbooks to say gravity itself is context-dependent, changing its behavior from galaxy cores to voids. The pinwheel doesn't just host this debate, it amplifies it, forcing us to confront whether our cosmic maps are missing invisible ink or whether the ink was never there to begin with. Every contorted star orbit whispers the same question: is the universe playing by different rules than we thought, or are we just missing the full story? For now, the pinwheel's dark knot remains a Rosetta Stone waiting to be deciphered. With new telescopes like the Vera Rubin Observatory coming online, we might soon have the data to tip the scales. Until then, Phenomenon 28 stands as a humbling reminder. Sometimes the cosmos's greatest puzzles aren't in the stars themselves, but in the invisible threads we're still learning to trace. From ghostly spirals defying gravity to stars hurtling through space like cosmic fugitives, the Pinwheel Galaxy has rewritten the rules of astrophysics before our eyes. But if we had to spotlight the 5 most mind-bending phenomena, they'd be these. First, the phantom arm. That wispy, impossible structure clinging to the galaxy's edge like a cosmic afterthought, surviving forces that should have torn it apart. Then there's the rogue pulsar with its erratic heartbeat, a dying star that can't decide whether to fade quietly or go out in a blaze of defiance. Don't forget the vanishing globular cluster, a million stars disappearing without a trace, leaving astronomers staring at empty sky where a stellar city once thrived. Phenomenon 25 takes fourth place, the black hole with X-ray fingerprints that hint at matter unraveling into quark soup, a state not seen since the Big Bang's first microseconds. And finally, the dark matter clump warping star path so precisely, it's either proof of invisible cosmic scaffolding or a sign we've misunderstood gravity itself. Each of these enigmas isn't just a cosmic oddity, it's a crack in the foundation of what we thought we knew. The Pinwheel Galaxy isn't merely showing off, it's handing us puzzles that could redefine dark matter, reshape stellar evolution, even rewrite Einstein's rulebook. And here's the thrilling part, we're only scratching the surface. Every new telescope, every advanced simulation peels back another layer, revealing just how much strangeness lurks in what we once called the ordinary universe. So now it's your turn. Which of these cosmic head-scratchers left you staring at the screen in awe? Was it the phantom arm weaving through space like a ghostly ribbon, or the black hole spewing physics too exotic for textbooks? Drop your pick in the comments, and if you're craving more deep space detective stories, hit subscribe. The universe is stranger than fiction, and together we're just beginning to uncover its secret.